Good morning. Thank you for being here, and I am happy to give this lecture on the co-design of far-field energy sources and battery-less sensors for the Industrial Internet of Things in the framework of the Wireless Power Transfer School. After a brief introduction and knowledge, I will recall the wireless technology that is suitable for the Industrial Internet of Things paradigm, and I will show the main technology challenges, such as low cost, zero power, identification, localization, and sensing. And I will show how the far-field reactive and near-field, the far-field radiative and the near-field reactive WPT system can be used in this environment. I will describe the main WPT matrix, and I will show some applications that has been developed at the University of Bologna, in particular an energy autonomous sensor that is able to being localized with high precision, and another one that is suitable for automotive application for wireless power and data transfer. And then I will come to some conclusions. I am from the University of Bologna, which is a multi-campus university. On my background, you see my town, my medieval town, but I am also active in the campus of Cesena, where a research group on WPT is located. But I would like also to remind you that my town is also the town of Guglielmo Marconi, one of the main inventors of the wireless technology. On the right side, you see his home in the countryside of Bologna, where he has developed a lot of his experiments, and it is now hosting a lab of the university. But it has to be noticed that the wireless was developed almost simultaneously by means of Guglielmo Marconi and Nikola Tesla. They were both researching on the radio wave propagation for wireless transmitting energy in the case of Tesla and information in the case of Marconi. And it is interesting what Tesla was considering at that time, when wireless is perfectly applied, the whole Earth will be converted in a huge brain, which in fact it is, all things being particles of a real and rhythmic wall, and the instrument through which we shall be able to do this will be amazingly simple compared with our present phone, which will be possible to carry it in our vest pocket. And it was a really visionary thought. So now we are experiencing the fourth industrial revolution. That means that the cyber physical systems deployed in both civil and industrial scenarios are able to continuously interact with the physical systems. And this is our main goal. And in this framework, WPT has been considered one of the strategic technologies of the next decades. But it is needed, together with this technology, the use of other enabling technologies, such as hardware ones related to 3D printing and hardware software related to the evolution and evaluation of such an amount of big data, such as big data analysis, machine learning, augmented reality, and mobile and edge computing. So what is the reference system that I am addressing during this lecture is a wireless system that can be suitable for the IoT. And I have shown here it as a puzzle of different subsystems realized by different technology. Besides the microwave system and the antenna, we will certainly need a radio to equip the system, but also a number of other subsystems controlled by a processor that are able to perform sensing and actuating capabilities, but also a part that is dedicated to the energy harvesting and the storage system. The requirements for this system are very stringent, since the dimension consumption must be extremely reduced. The consumption of power must be of the order of milliwatts, and the system, as I have shown, is requested to perform sensing, communication, and localization capabilities by adopting materials that must be eco-friendly and low cost. The idea of having such a complex system without any power source on board is possible because usually these kind of systems are requested to operate very few times per day. So on the overall, the power consumption can be from a few microwatts up to few hundreds of microwatts. And this is needed also and for this, also microcontrollers and sensors must be realized by means of ultra-low power technology. Energy harvesting for the Internet of Things can be performed from a number of ambient energies, such as solar, thermal, vibration, besides the RF. And as you can see here, the power density are shown for each energy source. RF is the lowest one, but it is the one that is always available, provided that some dedicated power sources can be located in the ambient. All the sources can be then combined by means of a power conversion process, and they can be exploited in the framework of a wireless IoT node that, as I said before, is composed of a number of subsystems. When we look at a wireless power transfer system exploiting time-varying electromagnetic fields, we can refer to the whole system as represented in this slide. We need to transfer from a side a certain amount of DC power to a remote side, that is the node side, where we need to exploit this DC power. So the process will exploit two kinds of conversion, a DC to AC conversion on the transmitter side and an AC to DC conversion on the receiver side. Then we will imply a front end based on both antennas or coupling device, depending on the technology adopted, and the WPT link. So there are a number of questions that need to be asked in order to realize a successful system. What is the power that it is needed on the remote side? Is it safe? And based on the system I am planning to design, is that the overall efficiency feasible? And what about the maximum distances to be reached, the directions, the frequency of operation, and the technology? All these questions will be answered by different WPT systems. The classification is now very clear, as you have seen also during the school. We can talk about near field non-radiative techniques when the source is located in the near field of the receiver. That means a few wavelengths or less than one wavelength from the receiver, while when they are in the respective far field region, so quite a few number of wavelengths, the technique to transfer the energy is based on far field techniques. The main difference between the two techniques is that in the near field there is a strong interaction between the transmitter and the receiver, while in the far field the receiver can be designed independently from the transmitter, since there is no significant interaction between them. The WPT, as I have said before, is a matter of efficiency. At the end, before proceeding to the realization of a system, one must ask himself, what is the overall efficiency? And from this point of view, the two classifications can be considered together, since we will have a transmitter, a receiver, a front end, end, which is realized in a different way if the reactive coupling of the far field interaction is exploited. But at the end, we must take into account the conversion efficiency of both the transmitter and the receiver, besides the efficiency of the link. And this can be approached in a unified way for both the approaches. But we are concentrating on the far field WPT and energy harvesting, and this is the case in which we need to distinguish what is the WPT system and the energy harvesting system. WPT system in far field means that we have some systems that are dedicated to provide energy on demand to dedicated nodes, that they will exploit this energy to operate. And this is the case of these two different systems that I have schematically depicted in these slides. The space solar power station concepts that our colleagues from Japan and from the US are studying in these days, where the microwave energy is sent from a satellite to the Earth by means of highly directive antenna. But also in this context, in the context of industrial Internet of Things, such kind of sources can be adopted to power up tags that then may be localized and may be interrogated for sensing purposes. So what is the building? What are the building blocks of a receiving system for energy harvesting or WPT purposes? It is the so-called Rectenna. That means an antenna combined with the rectified circuit, and the building blocks are for sure the antenna and the matching network between the antenna and the rectifier circuits, and also a very strategic aspect is role is played by the load, which is the optimum load, because as I will show later, the operation of a rectenna is strongly dependent on the load in terms of reaching the highest efficiency. So in many cases, in many battery-less nodes, the load is not a fixed one, but it is a dynamic one. It is managed by a low power management unit that is able to track the received power periodically and to keep the entire rectenna in its optimum operating conditions. So in the case of Rectenna for WPT, they may be used to provide, as I said before, energy in a very large number of environments, such as complex logistics, IoT, environmental monitoring, to energize not only in the Earth, but also in the space, to energize small rovers and drones. For energy harvesting, these rectennas can be used, for example, to power up remote wireless sensors, and that can also be wearable ones. So it has to be pointed out that the approach of a rectenna design, if it is used for energy harvesting or for WPT, must be somehow different, corresponding to the following criteria. In the case of a rectenna for wireless power transfer, so for intentional transfer of RF energy, we have a number of known data, such as the frequency source, the source intensity, the polarization, the direction of arrival. So the antenna requirements are typically for a single frequency, high directivity, linear polarization, and this task is of medium difficulty. While if the rectenna is designed for energy harvesting, usually the frequency source is unknown, and also its intensity is unknown, its polarization and its direction of arrival. So in this case, a completely different antenna should be designed. For example, a wideband or a multiband one, we need to accept a low directivity and circular polarization. So in this case, the antenna design is a demanding task. The overall design specification is, as I said before, the conversion efficiency of the system. So in this case, it is extremely important to have a very accurate evaluation of the power incident on the antenna, and so that both the matching network and the proper rectifying circuit may be selected as follows in the next slide. How can we evaluate the incident power? The incident power for a number of sources can be evaluated also by considering the electromagnetic theory and the reciprocity theorem, so that considering a scenario with different RF sources, with different polarization and different direction of arrival, the received power can be represented as, for example, an equivalent current source with the internal admittance representing the receiving antenna admittance. It has to be noticed that in this way, if we perform this computation by means of electromagnetic analysis, it is noticeable that we can take into account also the dispersive behavior of the antenna itself, plus the combination of the different tones that are incident on the rectifying circuit. Concerning the antennas, as I said before, we need to be extremely creative with respect to their topology, and depending on the scenario, we can either use a wideband antenna as the one I am showing here. They have a quite dispersive behavior with respect to the RF near field behavior and also the far field one, but they are wideband. Or we can use a multi-resonant antenna if we know that a certain number of sources at a certain number of frequencies can be used. This is, for example, a slot ring patch that I will describe in more details in a few slides. Or we can have auto-complementary antenna that are low dispersive with respect to both near field and far field. They allow good efficiency, but their drawback is the absence of the ground plane. So the performance are highly dependent on back material. And so this kind of antenna are not suitable for RFID applications or on-body applications. Once the antenna is selected, the harvester topology must be selected. And here we have three kinds of approaches that can be chosen. And there is one that is more suitable than the other one, again, depending on the scenario. We can either consider a single antenna and a single matching network for the purpose of providing the energy to a wireless sensor, but we can also choose more complex structures based on a number of antenna elements that can be combined at RF. Thus, the RF power is combined and it is provided to the input of the rectifier, or they can be singularly connected to a rectifier and combined in DC. We can refer to these two types of approaches as an antenna array or array of rectennas, and their performance are different. Since, for example, for the first time, we can design a plain antenna array, and so based also on its frequency dependent matching network, and then we can connect this antenna to the single rectifier. This solution is the good one if the direction of arrival of the RF energy is known, and since in this case we will exploit high efficiency from both the radiation aspects and the rectifying aspects. This is a very simple example of a 2D for element patch that are combined at RF, and then the part of the antenna is connected to the rectifier and the matching network. Another interesting approach that is used currently is the use of multi-element antenna of an array of rectangles that are then combined in DC. So each element can be located in a different position, and in order to capture the electromagnetic field from a different direction and with a different polarization. Each element and each rectifier will then have a relatively reduced efficiency, but if the design is performed correctly, any collected energy, DC energy, can be suitably combined in DC. The big problem to be solved is the fact that in this case, the antenna element can experience a strong electromagnetic coupling that can affect the behavior of each rectifier. Some examples are shown here on the right side. You can see the very famous solution that was found quite some years ago from the University of Colorado, from the group of Professor Popovich. On the left side, you can see a realization that was done from the University of Bologna, where you can see the collocation of 4 dipoles, 2 vertical one and 2 horizontal one, but also they are collocated with a complementary antenna, and this is the case in which the harvesting is performed at the UHF, while the sensing operation and localization are performed by means of ultra-wideband techniques. The last case is the case of a single antenna and a single rectifier. I have left this as the last one, since in this case the design of the antenna is quite complex, because we typically use this design when a multiband antenna is used. For example, the one I have presented before, the slotted patch ring antenna, where, for example, it can be designed with the slot dimension fixed in order to provide the excitation of one or more resonant modes of the antenna. And as you can see, the performance of both in the near field and in the far field of the antenna are shown here. It is noticeable that the radiation pattern for each frequency band of interest is different. So the Rectenna will perform in a certain direction with different, for example, conversion efficiency depending on the frequency that is currently harvested. This solution has been also realized, and the interesting thing is that in this case, a full wearable implementation of such a complex system has been obtained by using textile materials for both the substrate and the conductive part of the antenna. Also, as you know, it is extremely important the selection of both the rectifier topology and the diode to be used. Usually for energy harvesting for low power rectennas, a diode with has the best compromise between high saturation current, low junction capacitance, low ideality factor, and threshold voltage should be adopted. For example, a very popular one is the SMS 7630 that is widely used in the realization of the antenna of the rectenna for low power. And also the topology can be different, adopting half wave or full wave rectifier, or either voltage multiplier. The topology with many diodes are especially useful when high power are addressed, while and because each diode can introduce a small amount of losses that can be extremely negative in the case of ultra low power. On the overall, this plot can be adopted to decide the number of stages in your Rectenna. If the predicted RF power available are extremely low, perhaps one stage is the good solution, while if as the power increases, the rectifier can be realized by means of an increasing number of stages. As you can see, due to the performance, the nonlinear performance of the diode, for each stage there is a certain power at which the efficiency of the rectifier can be maximized. The Rectenna then must be designed as a wall. I am using now this full topology of the antenna, the RF combination of its performance. In this case, the antenna is circularly polarized. A multi-band matching network, the equivalent circuit of the received power together with the receiving antenna, and the rectifying circuit with its load. At this point, the Rectenna can be designed as a wall, and the load can be predicted and optimized in the effective operating condition of the Rectenna itself. On the other side, if multi-band is not addressed, and a narrow band design can be acceptable, we can also get rid of the matching network and try to design directly the antenna in order to match the complex input impedance, the conjugate complex impedance of the rectifier that is always characterized by a low resistance and a high capacitive reactance, as can be done in this case in order to get rid of the matching network that, as I said, for low power can lower the overall efficiency of the entire system. As I said at the beginning, particular attention must be put to the Rectenna load. If possible, instead of a fixed load, an ultra low power management unit should be adopted as the load in order to provide the optimum load of the Rectenna for a number of different levels of the incoming power. And thus the overall design of the Rectenna should replace the load with the baseband subsystem, and the efficiency of the entire Rectenna should be computed in terms of not only the RF to DC efficiency, but also including the DC to DC efficiency of the power management unit. And since this unit will change its impedance with the changing of the RF power, this unit must be included in the overall design of the Rectenna in order to provide accurate results of the whole system. A simple topology is depicted here for the power management unit. It is well known that the optimum load corresponds to a voltage, a DC voltage on the output that is approximately half of the open circuit voltage. So this topology is able to sample these voltages and to provide at the output of the rectifier the corresponding optimum load. This can be predicted by means of a sequence of analysis like this one, where the current, DC current and the DC voltage on the rectifier output are monitored and simultaneously the DC power is considered. As you can see, there is a certain value of the voltage and of the current that allows to obtain the maximum power, DC power at the output. It has to be noticed that for the same Rectenna, this varies with both the RF input power and the operating frequency. To conclude my lecture, I just wanted to show you very quickly some results obtained by designing energy autonomous wireless nodes. The first node that was designed, it was designed in the framework of an ESA project called Lost in Space. The challenge was to realize energy autonomous localization and tracking of objects equipped with RF tags, and this localization was requested to be with centimeter level accuracy. So the technology adopted was a combination of UHF and ultra-wideband for energy harvesting and localization purposes, respectively. The scenario that was implemented is shown in this case. The tag must be energized by means of a dedicated power sources that are these yellow objects, and there are also some anchor receiving nodes that when the tag is activated will interact with it in order to perform its localization. The main constraints are to comply with the ultra-wideband emission masks and to obtain a fine synchronization about the nodes, and to cover 10-meter range with centimeter level accuracy. This is the schematic representation of the system, where you can see both reference node and power transfer unit nodes are present, and the core is the design of the tag that must include both energy harvesting capabilities and ultra-wideband capabilities for localization purposes. For this reason, the tag building block is shown in this slide. As you can see, the energy harvesting, the Rectenna is the first front end of the tag, and the Rectenna is also able to provide energy not only to the main ultra-wideband radio, but also to a wake-up radio that is used for waking up the pulse, the ultra-wideband pulse generator, but also for addressing. The conditions of operation are very strict, since the tag must be activated with less than -17 dBm of received power, and it must provide an output DC voltage of more than 300 millivolts, with the power consumptions as low as 5 microwatts. This is needed to activate a ultra-wideband pulse generator that is on board of the tag itself. Very quickly, I will show the results. In this case, the same rectifier is used in combination with a voltage divider, a lossless voltage divider, in order to provide the high percentage of output voltage to the main radio, but a small one also to support the operation of the wake-up radio. Here you can see both simulation and measured results. As you can see, given the very accurate design procedure, the matching between simulation and measurements is very good. Here are some numbers for the performance of the tag that is whose picture is shown here. And as you can see, the first activation has been obtained with the power as low as 15 microwatts, with an open circuit voltage of about 1 volt. That corresponds to a received power of -13 dBm at a distance of approximately 10 meters. The maximum range of operation is larger, with received power of -16 dBm that is reached when the full tag is activated. The experiments have been performed in the ESA premises, where a Mars rover was tested and was successfully tested. Another example of the design approach that I have shown is this one that was foreseen for predictive maintenance in automotive scenarios. Even in this case, the RF on demand was foreseen. So as you can see, inside the car engine, miniaturized power sources have been located. They are based on a multi-antenna system that are used to distribute the RF energy in such a harsh electromagnetic environment. The wireless power transfer, in order to minimize these power sources, was selected to be at 2.45 gigahertz. Here is a picture of one of the antenna element. They are patches in order to take advantage of the ground plane, and they are circularly polarized. And in this picture, you can see the, the realized battery-less sensors. You can see on top the front view, on bottom the back view. It was realized in a very compact way, such as that is the overall dimension are 3 times 3 centimeters. On top, you can see the antenna with which was miniaturized by means of shorting pins, and it is used for energy harvesting. And on the same level, you can see some storage capacitors and a chip antenna that is used for communication purposes. And on the bottom side, you see the picture of the entire sensor node, including not only the harvesting part, but also the radio one. In this case, a LoRa communication protocol and chips have been used. The node operates in 4 phases. First of all, it is a startup, and there is the power on since the node turns on for the first time and communicates with the gates. There is also a sleep mode that will drive the node in ultra low power, and an active mode when the radio awakes and is able to exchange data with the gateway of the system. As you can see, some measurement has been carried out using the source illuminator and the tags. And here there are some representative results concerning the charging time needed from the tag to operate, and the mean power that was used in this representation. This concludes my lecture, and I am very happy to ask to your questions if you have any. Thank you.